Hello, everyone, and thank you for joining us. My name is Starlin with IFMA, and I'm happy to welcome you to our Wednesday webinar series. While we're giving everyone a moment to join and get settled, we want to hear from you. I'd like to remind you that this is an interactive session with time for Q&A. So let's go ahead and warm up our keyboards. Please share with us where you are joining from. I'm not going to ask you for something that I won't also share. I am joining from a hot and humid Houston, Texas. We have a very interesting and insightful webinar lined up for you today, and we are so glad that you are able to join us. This session is presented in partnership with Trane, and it is my pleasure to go ahead and introduce Adrienne Green from Trane, who will be kicking things off. Adrienne, welcome.
Thank you. Welcome, everyone. Thanks for joining our webinar, Building the Future, Exploring Key Business Drivers and AI-Enabled Controls for Smart Buildings. As she said, my name is Adrienne Green, and I'm part of the marketing team here at Trane Commercial, and I'll be moderating our call today. Just a few minor housekeeping items. Please put your questions in the chat throughout the presentation, and we'll have our subject matter experts answer those at the end. This recording will also be available for on-demand viewing after the event. And before we get started, I'd like to introduce our speakers. Josh Mullen is a product manager at Brainbox AI. He is on our product and solutions team. He has over 15 years of experience in various roles throughout this industry, all revolving around creating and quantifying energy, carbon, and cost savings for our clients. He has a passion for working on projects with complex systems, data-driven analysis and troubleshooting, and controls optimization. And we also have Dave Hostetler, our digital controls leader for Trane Technologies here. He spearheads the integration of digital and AI solutions to enhance customer outcomes. With over 13 years of diverse experience in the HVAC industry, he really specializes in controls, digital innovations, and energy management. His expertise spans local markets and national accounts within the Trane organization, and it really enables him to cater to a broad spectrum of customer needs. And with that, I'm going to hand it over to Dave to get us started today.
Thanks, Adrian. So we know that the built environment is in a really interesting place here in 2025. The last 5 years, our expectations of what we expect from buildings is probably changed faster than it has at any point in time. And it's not just the occupants of those buildings that are demanding that change. There's new technology like the things that we're going to talk about today that are driving that change. There are government regulations in terms of, depending on where you're joining us in the world, that are requiring that change. And then organizations have their own sustainability goals and pressures. And so you have this really interesting intersection of time that's driving this change for the built environment. And what that means is that standing still is really no longer an option for us, and that we have to do some things in buildings that we haven't done before. And so we know that buildings don't exist just to be a building. Nobody is out there building buildings because they like them. They have a purpose, right? Whether it's a hospital that is driving outcomes for patients, it's schools that are educating our children and those kinds of things. So the whole idea of understanding what the mission of that building is really foundational to us here at Trane. So before we jump into the why or the hows of the things that we're going to do, we need to fundamentally understand why is it that that building exists. And so we talked about, in my previous slide, this intersection in time, and how do we set up our buildings to be future ready? How do we position them knowing that this unprecedented change is going to happen? And this is across all of our vertical markets. It doesn't matter if you're in healthcare, commercial, industrial. This idea of positioning your building to be able to take advantage of technologies like we're going to talk about today, and ones that haven't even been thought of yet, is really important. And so all of that comes back to, how do you best position your building to execute the mission that it was built for? We talk about this in a lot of different ways, but this is another one of those sort of areas that cuts across every single vertical market, doesn't matter what part of the world that you're in, doesn't matter, sort of what that mission is. There's some common themes that we talk about in terms of aging infrastructure. So obviously, there's a lot more buildings that have been around for a few years than we're building brand new. Those brand new buildings get a lot of attention and a lot of headlines, but there's a really big existing building stock out there that we have to do something with. We have to be able to upgrade those buildings and make them perform in similar ways and in similar levels that the new buildings do. That's the expectation, right? Both between those government regulations that we talked about and occupants demanding they're going to demand that those aging buildings perform in the same way. And at the same time, we're doing that with a shrinking um, um, pool of people that can actually go out there and do this work, right? Here on the slide, we talk about a talent shortage, and this is really focused around HVAC technicians, but it's not just technicians that we have shortages of, right? When you look at the ancillary, sort of the next ring out of facility managers and energy engineers and sustainability professionals, there's not enough of any of those to tackle all of these things. So we have to look for tools to leverage the knowledge of those ones that we do have in the industry in a scalable way. And so when we talk about these challenges across the industry, and we look at the ways that organizations are expecting their buildings to improve, you can look at the things that are on here. So we want to obviously improve efficiency, reducing cost. And so you can look at that improving efficiency, reducing cost through a few different lenses, right? Is that absolutely about lowest dollars? Is that about the greenhouse gas emitted? So you can look at that achieving a similar goal through several lenses. Implementing sustainable practices and technology is also really important. And so again, you can look at that through a lot of lenses. We can say, is it on a sustainability scale, is it better to retrofit an existing building or build a new one? Well, we have to do that math and figure out, what is that sustainability really mean to that organization, and what are the expectations for their facilities? And then improving facility and system resiliency, right? So we expect our buildings to perform in a really wide range of challenges, right? So whether there's, depending on where you are in the world, problems with power or, grid shortages or demand response, we can talk about all of those kinds of things, but we expect that building to be resilient, for it to be able to perform against a really wide variety of conditions. And so we need to take all of those things into account as we, both position our building to take advantage of, the technologies like we're going to talk about today and the ones of the future. And so finally, for me, this is sort of how do we think about these things in terms of all of the different stakeholders for a building, right? Whether it's an individual building or a portfolio, the six things that are on here, and this is sort of the lens that we try to look through things as we adopt solutions in the built environment. And so when you talk about these different things, these sort of represent all the stakeholders for a building and all the things that people sort of expect out of them. And you can think about, some of these things are in natural harmony, that if you have a solution that addresses one of them, like energy savings, it sort of naturally pulls another one in the same direction. So for energy savings, like greenhouse gas reporting and reduction, if I spend less energy, if I'm using less energy, I'm going to reduce my greenhouse gas emissions. But there are some of these that are in perhaps natural tension, energy savings and occupant comfort. People hear that we want to save energy through, reducing HVAC use, and they hear, I'm going to be hot or cold in my building. I'm not going to be as comfortable as I was. And that's absolutely not the case. We want to have solutions that drive positive effects across multiple of these, even the ones that are naturally in tension. And so the whole idea here is that AI adoption is not the end goal, right? Again, the same way that we don't have buildings just to have buildings, we don't adopt AI just to adopt AI. But it's a tool to help us meet both the current and the future business objectives. And so this idea of getting connected and utilizing the data that your building produces in a beneficial way is the start of a journey. And so at this point, I'm going to turn it over to Josh to sort of take us into um, the next level down on how do we take advantage of this and how do we get started on this journey.
Awesome. Thank you, Dave. And hey, everyone, I'm Josh Mullen. I'm a product manager at BrainBox. For those who don't know, BrainBox was acquired by Trane, and we're a Trane Technologies company. BrainBox is really a company that leverages AI and machine learning to help optimize building operations. So today I'm going to do a deep dive in a few use cases and talk about all the nuances and how to get your building ready and um, the applications of machine learning and AI in the built environment. So as Dave mentioned before, and I really want this to be a take-home message, the environment and the applications of generative AI or AI in general and machine learning applications, that landscape is changing day to day, and it's changing very rapidly. And by and large, for the most part, AI and machine learning applications in buildings are limited only to the amount of use cases you can dream up. And Dave mentioned that AI adoption should not be the end goal. AI and machine learning should be leveraged to fit a use case because without a use case, you can't measure the results and you can't quantify the impact or the ROI or if it is or wasn't effective. And then the other huge take home message that I want to leave you all with is whatever application you're doing, um, the AI and machine learning outcomes are only as good as the underlying data it leverages. I had a professor who was a system dynamics professor, how to model dynamical systems, and he would always say like it's inefficient to infer reality from its shadows. That's a very like professorish way of saying without the data, it's super, super, super hard to get the correct model and to get the correct results that you want. So as you're looking at your building and as you're looking to start leveraging machine learning or leveraging AI for whatever use case you want to apply it to, you first need to look at what the underlying data needed for that use case is, and then what the quality of that data is, and making sure that it is fit to meet the purpose and the needs of it. And we'll go over what those data needs are in each application that I talk about here. All right, so I mentioned that, my company is really a technology focused company. We're leveraging advanced technology, be it machine learning or AI or other means, um, to really optimize building operations. And we view building operations of having two large components, energy and maintenance. And on the energy side, we have what we call autonomous AI. That is the brand term for what the industry calls advanced supervisory control. And really, what that's focusing on is optimizing the HVAC control sequences. And we're looking at optimizing the sequences, the schedules, and the set points of those systems. However, if those systems aren't well maintained, they will never be able to meet those optimized sequences, right? So the other half of the coin is how do we ensure that those systems are in proper running order, and how do we make that physical maintenance as efficient as possible so more and more of those pieces of equipment are in tip-top shape. And with that, we have a tool that is agentic AI, or an LLM agent that goes out and it puts together different pieces of the operational practice of physical maintenance. So, it's pulling together the telemetry data coming out of the BMS, looking at the fault codes, pulling up troubleshooting manuals, getting all that data into one place so someone can quickly explore it and go through those troubleshooting steps as quickly as possible to be as efficient as possible. And I am going to step through each one of those use cases, the advanced supervisory control, and then the LLM application as it relates to physical maintenance, um, and go through the underlying what it is and go through the underlying data requirements. And hopefully you guys will have a lot of questions and there'll be time at the end that we can roll through those questions and dive a little deeper. Okay. So first, what is advanced supervisory control? Well, first and foremost, most advanced supervisory control is designed to optimize energy consumption while maintaining or improving occupant comfort, right? It's not enough just to turn everything off and have people be uncomfortable, but we're really looking at optimizing how those pieces of equipment operate so everyone is comfortable, but it's using as little energy as possible. Other use cases, and these aren't all the use cases, these are just some use cases of advanced supervisory control, is automated demand response, functional performance testing. So let's say you're doing seasonal maintenance. You have a portfolio of um, big box stores that have 40 rooftop units on each one, and you want to do seasonal heating or cooling checks. So at night, you want to run those pieces of equipment through each stage of cooling or each stage of heating and issue that technician a report so they know what they're getting into when they go out there. And then after the work is performed, you want to be able to run that equipment again at night so no one is interrupted, no comfort is affected, and check to see if that work has been performed properly. There's also flexible load management. So that comes in the form of load shaping or load shifting based on a third party signal coming from the utility or coming from the grid itself. And then cost optimization. Energy consumption is only one portion of your electric bill. There's also the demand portion. So how to limit demand while still adhering to all of the comfort requirements. And in order to do that, we're looking to pull three main levers. Those levers are schedules. So when should the equipment run? Set points. What is the goal of the equipment running? And then finally, sequences. How do the systems operate to achieve those goals? And we're going to dive into, just so everyone's quickly on the same page, we're going to dive into what I mean when I say we connect to buildings. So here, and forgive me, I don't have a laser pointer to point out things, so I'm going to describe it. But here is an overview of a traditional HVAC control architecture. So at the lowest level, you have your field level controllers, the sensors, so the room temperature sensors, supply air temperature sensors, static pressure sensors. And you also have your actuators. Then those communicate up and down to field supervisory controllers or supervisory controllers. Those supervisory controllers have more advanced sequences and set points that tell those systems what to do. And eventually, all those supervisory controllers typically roll up to an overarching supervisory controller that displays the graphical user interface that people can adjust schedules and set points, and it has even more complex sequences in it. When you are an advanced supervisory control layer, you're either connecting to the IP network and talking to those supervisory controllers and subcontrollers directly, or you're being installed as a software package on a Jace or the BMS supervisor. You can also communicate via an API if the client has an independent data layer. Um, and what I mean by an independent data layer is more and more large portfolios are starting to adopt this practice. So they have many, many, many different BMSs and buildings, and they're pulling those different building data up into one central cloud. They are normalizing all those data points. They're creating data models for it. They're combining it with different metadata about the data points. So be it asset data of the equipment that you're controlling or any other useful information around it. And they're normalizing what those points are called. Then they're making it able to be accessed via an API by different third parties. This is a lot. It's a lot to take in. I'm just trying to get everyone to understand that this is we're starting to see this more and more in large businesses, and a lot of people are trying to adopt this independent data layer model. However, it's complicated and it puts more onus on the independent data layer to ensure that, say, we want to write to a set point. Now they have to take that write ability and make sure it trickles down into the sub-level controllers the right way. And we'll get into the nuances there, but just getting everyone to understand that. And often people approach me and say, like, I have an independent data layer. I'm ready for advanced supervisory control. What do you need? And my answer to them is always like, okay, can you share metadata about the points? Can you share the equipment data about the systems that I'm controlling? And can you easily share the data models of the data in your data lake or your independent data layer? And what I mean by that is how the equipment is connected in a hierarchy. So what VAVs are connected to what RTUs or what air handlers, and what air handlers are connected to what chiller plants. And if you can't communicate that easily and have it easily shareable, then you don't have a functioning externally facing independent data layer. All right, so regardless if you're communicating independent data layer or if we are connected onto your control network, for advanced supervisory control to happen, we need to be able to read, we need to be able to write, and we need to be able to release those rights. So for the reading, most advanced supervisory control or most advanced supervisory optimization platforms, they need to be able to read data every 5 minutes. Sometimes with chiller plants, it could be as fast as 1 minute. And then they need to be able to write to set points and schedules and other control points. And what's really important is that command needs to persist. So it either needs to leverage the backnet priority array, so that command sort of has override ability and is taken into account and the system follows it, or some other means of overriding. It could be that it's a timed override at a high level priority. Um, but what's most important is when you write to a set point, that set point actually is the set point that is inducing that equipment behavior. So if you're trying to write to the static pressure set point, that fan should modulate to meet that static pressure set point, and it shouldn't actually be referencing another static pressure set point in the background, right? And then finally, all advanced supervisory control should have guide rails, and it should have the ability to release control for whatever reason, whether it is internet connectivity, whether there is some problem with the system as a whole, like the room temperatures are too hot, or there's a fault in the unit. you want to release the control to make troubleshooting really easy and give the control back to the BMS. And you can do that either by having the timed overrides being sort of just decay, or you can do it by nulling out the commands. It's all, it's dependent on what advanced supervisory control provider you're using or leveraging. And finally, okay, we went over the read, write, and release, but how does this work in practice? Well, you connect to a building, you pull in that telemetry data, that data coming from the BMS, then you marry it with granular weather data, your grid emission data, your occupant levels. Those can be coming from, third-party occupancy sensors, Google Popular Times, whatever occupancy data you have. Also pulling in the utility tariff structures. And we use this information to inform our algorithms, and we use this information to train our machine learning models. Our machine learning models at BrainBox focus on predicting the space temperature 1 to 6 hours ahead, and those predictions then are used as inputs into our models to control the equipment. Other ASO or ASC applications could do it differently. This is just how we do it here. And a deeper look into how we do it and what we do. As I covered for the inputs, we're looking at very granular weather data. Like weather is the largest component in how a building, in explaining the variation of energy consumption in buildings. So we want to know what the weather is and what it will be so we can predict out to the future what the space temperature is and what it will be. And then we also need the telemetry data every 5 minutes coming in. We need cleaned data. So, we're taking all these different BMS points and we're normalizing them. We leverage Haystack. You don't need to, but you should do some tagging, whether it is brick or haystack or whatever, just so you can get a unified data model so you can easily apply machine learning models to it. We have been leveraging neural nets with ordinary differential equations guiding them. This is called neural ODEs. We have recently found that it leads to shorter training times and training data requirements and a more robust model. And then the output is the space temperature prediction. And how that all gets pulled together is I went through how we're able to leverage the space temperature predictions. So those space temperature predictions are put into our algos. One of our algos is Chronos. It's really focused on optimum start and optimum stop. It's taking that space temperature prediction for each and every zone. Let's say for its multi-zone VAV system that has electric heat and a rooftop unit. And it's using those space temperature predictions to figure out when to start, which VAVs it should operate first and pull on or hold off for a little bit longer, when to turn the system on as a whole, and then how much reheat should it turn on and at what time. And the same is happening at the end of the day. It's seeing how long it can drift the building for and still meet ventilation requirements or whatever the guidelines that the customer has for us. Okay, and we often hear when we get into it, yeah, but I already have optimum start, or I already have static pressure reset in supply air temperature. And that's true. Like we go into a lot of buildings that already have this, and what we're finding is generally either it hasn't been commissioned properly, or they are missing some sort of input necessary to do true optimization and get more granular savings. So here's an example of a building that had optimum start and had supplier temperature and static pressure reset. It was a self-contained multi-zone rooftop unit with electric reheat, and you can see it's slamming on in the morning. 45-ish kW morning warm-up peak. And then with us, it's no longer slamming in the morning, and the total peak is a lot lower at like 30-ish. So we're reducing not only the morning warm-up peak, but reducing the overall energy consumption throughout the day as well. And here's another look at the data, just a different way. This is time series data. These are the periods of time that BrainBox is on. Here's the outside air. The blue line is the outside air temperature. I'm realizing you can't see my mouse. And then the blue colored portion is, the portion that we aren't in control for. And you can see that the energy consumption as a whole is just much greater. All right. So right there, I took you guys through a crash course of advanced supervisory control and advanced supervisory optimization. I'm sure there's a lot of questions. Now for the remaining time, I'm going to talk about leveraging generative AI to make physical maintenance more efficient. So first, we'll start with the data. So the data considerations for a generative workflow AI application is first and foremost raw data, okay? And you need to decide on the data sources that you want to leverage. Then you need to get the data pipes into it and make it available to the LLM. You need to process the data. So, what is this data? How should I look at it? What metadata can you associate with this data? What can I tell the LLM about this data? Then you need to be able to have the LLM be able to interact with it. Give the LLM access to tools, because an LLM is a probabilistic model. So it's going to answer based on probabilities, but sometimes you want a deterministic answer. And when you want a deterministic answer, you want to give it access to tools. So it doesn't have to like give you a probabilistic answer. It can give you an exact answer every time. And then from that, at the end of the funnel, you get enhanced insights. And data input examples for an application like this would be asset information. So what is your equipment asset list? What is the telemetry data of that asset or those pieces of equipment? What does the work order data look like? And can you associate the work order data with that asset information and that telemetry data? Then parts information. So the parts for that equipment, can the LLM quickly identify what are the replacement parts for it? If you have AFDD data, that's a wonderful thing to pull in. And then manufacturer error codes, the fault codes on the BMS or the unit as a whole, and then troubleshooting guides. O&M manuals and manufacturers have tons of troubleshooting guides. They're typically tomes. Having an LLM quickly identify how to troubleshoot the equipment based on that manufacturer data really speeds up time. And then for an LLM in general, you need a foundational database. So this is what you train the model on. Do you want to give it access to HVAC documents and building science documents? Do you want to give it access to the O&M manuals and the repair manuals? Like giving it access so it has context to answer your questions is important. Giving it access to tools. So maybe you do scope 1, 2, and 3 reporting. Well, you don't want to have the LLM have to constantly try to figure out how to do scope 1, 2, and 3 calculations. You want it to have access to a tool that already has those calculations in it and can quickly grab them and iterate that data for you, and then allow the LLM to have access to it. And then human in the loop agents. So you want the ability to give it feedback. And anytime you are pushing to a system, you want to have a human in the loop in it, whether it's to change and modify, set points on a BMS, or if it's to change and modify a work order, right? You can automate that through an LLM, but you want to have the ability for the human to say, yes, do this change, or no, don't do this change. And then knowledge-based resources. So again, this is what data are you having at access, and what data do you have available to it. And then if you have all those disparate data sources available to it, it can be a very, very flexible tool. It can help you with reporting. It can help you with fault detection and diagnostics. It can help you with, um, you know, troubleshooting and field maintenance. It can help you with building control and execution and troubleshooting. All right, I went through those two applications. A lot of times people ask the question of like, okay, yeah, it's easy for me to do something and deploy machine learning or AI in a building, but can it be scaled? And the answer is yes, it can be with careful thought about the infrastructure and how you would deploy the building and how you would deploy your solution. And this is our use case. It's a biopharmaceutical organization. They have very, very strict um, space temperature and relative humidity requirements, both occupied and unoccupied. They have over 200 locations all across the US. Um, their goals were to maintain precise control, but save of the temperature requirements, but optimize overall energy consumption. They have a larger goal of, reducing their greenhouse gases by 40%, and they want to be net zero by 2035. And they enlisted us to do um, advanced supervisory control, or our autonomous AI solution. And we have been in their portfolio since 2022. I'm sorry, the years are creeping up on me now. And we have had a considerable impact, right? And this is a tool in um, to help them meet their goal of getting to net zero. We are, bringing their greenhouse gases down. We're saving them money, and we are having a positive impact in their building, and we're helping them along their journey, right? And it's been a years long process, but we have made steady and steady gains each and every year, and we keep improving every time we modify or improve our control algorithms. We get the client more and more savings. So that, in a nutshell, is it. It was a lot to take in. I'm sure you guys have questions, so we'll roll into the question and answer portion. Does that sound good?
Yes, wonderful. Our first question, gentlemen, comes from Sharon, and it's a inquiry if this application is in use in higher education, and if we can share about some of the universities or colleges that are using this application with their multi-site buildings.
Yeah. So Dave, feel free to chime in on this because you're more in tune on the commercial side, but we do have a few uh, buildings in universities. We aren't in a full, like, entire university yet, but we do have we are in buildings. We can get you information about that.
We've engaged with a lot of universities, and we've got some initial projects going in some of those. And then one of the things that's really interesting when you work with universities is they tend to they want to blend their goals about improving the performance with their buildings with their mission, right? So back to the thing that I talked about at the top of, these buildings don't exist just to be buildings, they exist to educate students. And so I don't know of any university that's out there that's not looking to expose their students to real applications of AI and how it's, affecting the world that we live in. And so the biggest one of the asks we get, and we're working with some universities to sort of maybe develop this content around how do we not only improve the performance of the buildings, but how do we expose those students in those universities to the ways that we do this and help them learn, and as they learn computer science and AI and coding and all of the things that universities are doing now, expose them to the real world impact of what they're doing. So we love working with those universities, and they always bring really interesting use cases. And every university is a unique collection of buildings, and universities present some interesting challenges. But we look forward to meeting those and publishing some case studies around some of the ones that we are working with.
Wonderful, thank you. Our next question comes from Dean. When scaling regionally, how do you handle buildings of varying age and types of systems, etc.? Dave, do you want to take us with a starting point, and then Josh, you could jump in?
Yeah. So I think if you're talking about scaling regionally with a specific customer, right? Like there's a set of data that we need regardless of what we're doing, right? But one of the things within an individual customer that has, a portfolio of buildings, the thing that doesn't change, that makes our job a little easier is generally their expectations are consistent, right? So we don't have to go back and discover what are the expectations for this building or this building or this building. We know that part. And so what we have to do is then plug in, okay, how are we going to meet those expectations? And it's sort of we have to do that data cleanup and the data, that Josh talked about. And he talked about we use haystack tagging for data normalization. And this is really something that we want to drive home, this idea of, if even within a portfolio of buildings that all look alike, right? If they're installed over time, the data still isn't going to be exactly the same, right? So the supply air temperature point in one building is not going to be named exactly the same as it is in another one. So this idea of data normalization across a portfolio is really, really important. And once we do that, and that's a non-trivial step, right? Like I don't want to hand wave that and say that that's easy, but but understanding the customer's expectations for their buildings sort of globally, and then performing that data normalization, I will say ruthlessly, and making sure that we do that really, really well, is what allows us to have a solid regional deployment or national deployment.
Yeah, and I'll add that like our algos are system specific. So depending on the vintage of the system, we may or may not have an algorithm that can, optimize it. Like VVT systems, variable volume and temperature systems, those are like archaic systems that we don't really have a focus on optimizing, because we'd much rather optimize like the current systems, the multi-zone VAV systems of the world. There's also like, yeah, we'll look at the points available across a portfolio and talk to the client about like, is it ready or isn't it? It's not uncommon, especially in large commercial real estate, that they will have buildings that still have pneumatic control, right? And it's a surprising amount of times I've had to have a conversation in my career explaining that we cannot see pneumatic control on a BMS, right? Unless it's a pneumatic to electronic overlay. Like I don't know what your pneumatic systems are doing, and I can't control them electronically, right? So it is a something that we do look at very, very carefully.
Thank you for that question, Davida. That was great. We have another question. If a damper is stuck, can AI detect the fault and auto adjust other settings to maintain conditions until it's fixed?
Yeah, and so I'll answer this in two different ways. First, there are companies that strictly focus on fault detection and diagnostics. That personally is not BrainBox's bailiwick. We're not focused on that. I'm sure this is one of the applications of predictive maintenance that other companies are working on. However, for our supply air temperature and static pressure reset algorithm, we do have rogue zone detection in it. So if that damper is stuck for whatever reason and it is indicated and flagged as a rogue zone, we will take it out of the algorithm so it doesn't keep ramping the fan up to meet that space temperature set point, and we can inform the client on it. But um, it is not leveraging, generative AI or anything of the such there. Dave?
Thank you.
And I was going to say, so that, and the if the question was, and I think Josh answered it well there around like where it is today, but we're the technology, and this is not the brain box. This is the technology generally is not going to say, the damper is stuck in this room, so I'm going to overcool the two rooms next to it to try to drive that, keep that one space comfortable. That's probably, future case and, state of where this technology is going to go. And it's a great example of, what we talked about at the top of, implementing the AI of today is not the end state, right? Like that's, as we continue to evolve and we have a larger and larger set of clean data that we're leveraging to drive the outcomes that we can drive today, that's going to allow some of those possibilities of, hey, over time we've seen this, and it's going to, as the AI matures, allow us to do some of those other things.
Wonderful. Thank you. We have another question around, do current AI models allow for the expansion of digital twins to achieve greater control and management in the field of facility management, or is it too early?
Similarly to the way we answered the question before, when we talk about digital twins, and digital twin is a really interesting, term, when you talk about, the levels of digital twin and what that actually means. And then, but, the expectation of a digital twin, at its highest level of being able to, do predictive, this part is going to fail at this point in time, and, those kinds of capabilities. Can we do that at the building level yet? No. But what we can do today is utilize the data that we're using for autonomous control, or the supervisory control that we're talking about, to inform the models that we use to model building performance. So if you're doing a retrofit and that kind of thing, we can use the data of, hey, we never needed stage 3 of cooling on that rooftop. We never needed, so we can use that data to better inform those models, but it's not all the way to where we can build a digital twin of an entire building and predict, performance at sort of that level of, of granularity, if you will.
Yeah, and I'll add to that, Dave. So like I'm with you. I think digital twin is a term that has multiple different meanings. So my take is like, take the biopharmaceutical that I presented, right? I don't know if the term is digital twin or not, but what advanced supervisory control allows you to do is it allows you to take a bunch of different systems and make that are being controlled all different ways, right? Like each building had its own, it's they're all across the US. They had their own control team implement the controls in those buildings. They did their best, they commissioned them, but advanced supervisory control allows you to go over top and be like, I am going to apply the best practice supplier temperature and static pressure reset, or I am going to go and over the top and apply the best practice optimum start and optimum stop algorithm, leveraging machine learning for that specific building, for that specific zone, again and again. And you saw the impact of that across those buildings. Now the savings in each one of those varies based on how optimized the controls were in the buildings, but overall, we're having a very large effect.
Thank you. We have another question. How does AI handle real time decision making when balancing energy savings with occupant comfort?
Yeah, so just really easy. Occupant comfort are the goals of any AI algorithm or any machine learning algorithm. So those are the goals and the boundaries that it's told to stay within, right? Um, so for instance, for optimum start, you want to get in between your occupied heating and occupied cooling set point at the time that that occupants are in the building, right? So it's not going to, you know, start 5 degrees cooler or 5 degrees warmer than it should. It's going to try to be within those bounds.
Okay, wonderful. We have another question. We are going to go over how can AI enabled controls specifically enhance energy efficiency and sustainability in modern smart buildings?
Yeah, sorry. That was a question. I'm sorry, Adrian.
Yes,
I was
I'm so
reading
sorry. Let me
something.
repeat that.
My
How
bad.
can AI enabled controls specifically enhance energy efficiency and sustainability in modern smart buildings?
Yeah, so it is a tool that can be leveraged. I want to say that, like, you know, and Dave and I will be the first to say, like, advanced supervisory control, AI enabled controls, or generative AI on the field maintenance side, that alone won't get you to net zero, or that alone won't get you to all your sustainability goals, right? It needs to be a tool that you use to help you get there, but you'll need to look at electrification. You'll need to look at how to acquire clean energy, or you know should you invest in on-site or off-site renewables. There's like tons of additional things you can do to get you there, but optimizing your controls is a path there, and it is an important component of it.
Think this is like, if we think about buildings on a spectrum, right? And we start from, all the way at the left-hand side, a building, I'll say an older building, maybe pneumatic, running 24/7 all the time. And we think about, the actual goal of that building is to be, comfortable in the space from 9 to 5, right? And so you start from a building that just runs wide open all the time, and every step you take, to adding so pneumatic controls or DDC controls with optimum start, DDC controls with, it adds a layer of complexity, but you're approaching, what I'll call the physical limit of, what you can do to achieve the comfort you want in that space. At some level, you have to move heat in and heat out, right? Like whether um, to the space. And so and when you talk about a modern smart building and the level of programming and control that you have to do at that, you sort of um, you end up with this level of complexity programmed into those field specific controllers and the application controllers and those that becomes almost problematic at the building level, where it becomes easier to deploy at scale using AI. So it's less rule based, the programming that we're used to in building controls of, if this happens, then do this. And leveraging, the compute becomes problematic in a smart building. And so to get those last few steps towards what I'll call the limits of physics, right? Like AI becomes a better tool in our arsenal than trying to program, really, really complex sequences within the building automation system.
Thank you so much. I have time for one last question. So we're going to go with what are the key business drivers that are currently influencing the adoption of smart technology in the built environment?
Yeah, so there's a couple, right? Like, and we see these in a few different ways. Obviously, the one that jumps out at people the most is they want to spend less on utilities, right? They want to write a smaller check to their utility company every month. Whether that's in the form of, lower consumption, so using less energy, or lower demand charges, so change not just lowering consumption, but changing the way that we use energy and the times that we use energy. That's probably the most, immediately obvious and the one that, people come to us as. But there's a lot of, companies that have made really aggressive sustainability commitments, both publicly to their boards, to, whatever it is. And they've taken, the easy projects are done, right? Like, you don't see many T8 fluorescent bulbs anymore. You walk in and there's it's all LED. So everybody's done the lighting projects. They've done maybe some equipment upgrades. They've done some of those things, and it hasn't gotten them all the way to their goals. And they need to draw the path of, how do they get to net zero, or to, whatever those goals are by 2030 or 2040. And so they're starting to figure out that we're going to have to do some more aggressive things. And one of those tools in our arsenal is this supervisory control, and as Josh was talking about, also taking care of some of that deferred maintenance, and making the people that are going to go turn wrenches and fix equipment and bring equipment back to, optimal efficiency, making them more efficient. And we're going to have to do, it's an all of the above approach, right? And so when we talk about AI and its, impact on those six areas we talked about at the top of in the wheel, all of those things are key business drivers. Again, the shortest path is usually that I'm spending too much on utilities, but all of those things are drivers that are going to push you towards a solution that allows AI to help you optimize your building.
Great. Thank you so much. Josh and Dave, we really appreciate you sharing with us today. As a reminder, this presentation is going to be sent out via email to watch on demand. If anyone is interested in Trane's Future Ready Buildings Report to learn about the 8 business drivers advancing building technology, to dive a little further into what Josh and Dave shared today, please feel free to visit the link on the screen, trane.com/future-ready, and you will receive a playback link in your email later today for anyone who's interested. Again, we appreciate your time. Thank you for joining us.